This is a reassessment on Gauss's and Ampere's law. This question wants us to use Gauss's law to determine the equation for the electric field near the center of a very large uniformly charged plate. The area of one surface of the plate is A, and the total amount of charge on the plate is Q. So if we draw this as the large plate, we can use the Gaussian surface as this square, and I have it protruding out. So we have an E to the right and an E to the left. And this A box is this here. So as we can see, drawing the in hats, they're going to be zero. We're going to get a zero flux everywhere except on the ends, because they're parallel on the ends, but everywhere else they're perpendicular. So we're going to assume that E right equals E left, so we're just going to call that E. And so we're going to calculate the electric net flux by doing the regular calculation, E dot n hat dot dA. So since we have E to the right and E to the left, that's going to be 2E. We have a cosine of 0 since they're parallel, times A of the box, which we said this was A of the box since that's our Gaussian surface. So total area is going to be A of that box over A, which they told us that one surface of the plate is A. That's the area. So that's going to be the total area, and the charge inside the box is going to be just Q times that, because they also told us the total amount of charge on the plate is Q. So now we can apply Gauss's law. We calculated this as the net flux. That's going to be equal to the charge inside, which we also just said was this, divided by epsilon naught. Now when we solve for E, we're going to divide by A box and 2, and so A box is going to cancel, so that actually doesn't take into account when we're solving for the electric field in this case, and we just get Q divided by A all over 2 epsilon naught, and that's the electric field in this case. And as you can see, it was a pretty simple calculation because we used the Gaussian surface. It made it a lot easier.